Okay, so this video is going to finish up the review, excuse me, for pre-algebra that covers sections 4.5 and 4.6 so that you can go ahead and take the quiz on these two. So I'm on the second page, page 58 of the number theory student activity worksheet that I sent home. So we're working through the odd problems. And in this case, we're starting with number 17, and we end up being asked to find the first 5 terms of the following recursively defined sequences. So remember that a recursively defined sequence means that you are given a term for position 1. So this starts your series, your sequence, and then you're given the formula that any term at position n is equal to, pen stopped working, 2 times the previous term. And so in this case, we were given a1, so we know that the term at position 2 is equal to, and so that 2 becomes our n. Remember that n just stands for the position number, 1, 2, 3, 4 to infinity, whatever position your term is in. So the term at position 2 is equal to 2 times the term at position 1, which we're given above is 4. So the term at position 2 is 8. And then we just keep going. The term at position 3 is the term at the previous position, which is 8. Well, let's do 2 first. 2 times 8. So keep the same format. And we find that 8 times 2 is 16. And then the term at position 4 is the 2 times the previous term, which is 16. So we're looking at a geometric formula or geometric sequence here. So 2 times 16 is 32. And then our last one, the term at position 5 is 2 times the previous term, which is 32. And we get 64. And we are done. Our sequence is 4, 8, 16, 32, and 64. Okay, number 17. So, 17, number 19, sorry. Oh, it's the end of the day. Number 19 gives us the recursive definition of term of position 1 is 2. So our sequence starts with the number 2, and then we can calculate the rest of the sequence with the formula an equals -2 times an minus 1. So a1 is 2, which means that the term at position 2 is -2 times the previous term. Now remember, this whole thing, a1, that is the term that you're calculating or that they give you. The 1 is the position number. This is going to be important when you look at, or when you're working on the quiz. That's your position number. So if you ever have an equation with n as something you are multiplying or adding, then you look at your position number. You're going to multiply or add the position number. So going back to this one, a2 equals -2 times the term of the previous position, which is 2, and a2 is -4. Position 3 has -2, which in this case is our ratio, times the previous term, which is -4, and we end up with a +8. Again, another geometric sequence. A4, the term at position 4 is -2, always, times the previous term, which is 8, and we get -16. And then the last one, the term at position 5 is equal to -2 times -16, which we know a negative times a negative is a positive, and 2 times 16 is 32. So our sequence is 2, -4, 8, -16, 32. Excuse me. Okay, number 21. 21 and 23, we are being asked to write the recursive definition for the following sequences. So that means we need to define a1, the term at position 1, and then we need to write the simplified equation formula that we need to solve any other term in the sequence. So they give us 3, 6, and 12. This is our sequence. And we know that this is a geometric sequence because we know if we multiply each term by 2, we get the next term. So 3 times 2 is 6, 2 times 2, or 6 times 2 is 12, and then 12 times 2, so on and so forth. And we can keep doing that up to whatever term we want to, but we need to instead write the recursive formula that explains the sequence. So first let's define A1, which we know the term in position 1 is 3. And then because this is a geometric formula, we need to define our ratio. And so your ratio is what you're multiplying by. So in this case, it's a positive 2. All right, so, excuse me. The recursive formula is that the term at any position n is equal to the previous term times the ratio. So let's plug that in and we get an equals an minus 1 times 2. But to put this in proper mathematical form, you stick that constant in front of your variable. So because it's a coefficient, so it's just an equals 2 times an minus 1. So your final recursive definition is the term at position 1, and then the formula an equals 2an minus 1. It's kind of messy. All right, let's do that one more time. 23. Number 23 gives us 16, 8, and 4 as our sequence. All right, so again, we have a geometric formula, although you can notice your numbers are descending in value. So this means that you are multiplying times a fraction, and that fraction is 1/2. We know that 16 divided by 2 is 8. 8 divided by 2 is 4. And if we continue that, we'll continue finding the sequence. Excuse me, I got choked. I can't stop coughing. Okay, so define A1. Well, you can see that it's 16. Then let's look at our equation. What's our ratio first? Our ratio is 1/2. Okay, so that's done. So your base formula, recursive geometric formula, is an equals the previous term, an minus 1 times r. So our equation is an equals an minus 1 times 1/2. And so you can write your final equation. Well, I would keep it simple. Again, just put that in front as the coefficient. An equals 1/2 a sub n minus 1. So that's an equals 1/2 times the previous term. And then of course, add your definition for the first term in your sequence, and you have the entire recursive definition for the sequence. All right, 25. So number 25 and 27 ask us to write the explicit formula for these sequences and then find the term at position 10, A10. So we are given the sequence 2, 6, 18, 54. And when we look at this, we can see that it is geometric. 2 times 3 is 6, 6 times 3 is 18, 18 times 3 is 54. So we know that our A1 is 2 and our ratio is a positive 3. These are going to give it escalate quickly, right? So our explicit formula for geometric sequences is in our books. Let me get it in front of me so I write it right. Okay, so we are looking at geometric explicit formulas. So this one is an So the term at any position n, that's the position number, equals the first term in the sequence, which is in position 1, times the ratio raised to the power of the previous term position. Let me say that again. So the term at any position n is equal to the first term in the sequence times the ratio raised to the power of the previous term. That's what that n minus 1. And sorry, I should say raised to the power of the previous position number, right? That's what n minus 1 is. So let's plug in what we know, our A1 and our ratio, into this equation. And we find that n, so the term at any position n, is equal to our first term, which is 2, times the ratio 3 raised to the previous position, the value of the previous position. Okay, now let's see that in action. Let's see what we're talking about. So if we're told to find the term at position n, remember, n is always n. So if we establish that the position we're trying to calculate the term for is position 10, that means that in our equation, anywhere we see the variable n, we plug in the position number. So if we're calculating the term at position n, that is equal to 2 times 3 raised to the power of 10 minus 1. And you can see how that 10 minus 1 is the previous position number, because what comes right before 10? 9, right? So we have 2 times 3 to the 9th. And when you calculate all that, obviously you want to make sure you calculate your exponent first. So you end up, let me just give you that number because they don't in my book. So when you do that, you find that 3 raised to the power of 9 is some big humongous number. It's 2 times 19,683. I told you this escalated quickly. Therefore, the term at position 10 is times 2, 39,366. So your final answer here is first your explicit formula, which is AN equals 2 times 3 raised to the power of the equal to the previous position number, and A10 equals 39,366. And that is your final answer for number 25. Forgot my number. Okay, let's do this again. Number 27. So for number 27, our sequence is 1024. I'm going to use semicolons. 512, 256, and 128. All right, so first off, you can see that these numbers are decreasing in value. And also, hopefully, you can see that these are a geometric formula. So you're multiplying, or in this case, dividing. You can say it either way. You're either multiplying by a fraction, which by definition means you are dividing by the denominator of that fraction. But so in this case, definitely geometric. So we know it's geometric. And so we know we're going to have a ratio. So our ratio is 1/2. And our first term is 1024. All right, so let's get our base explicit geometric formula is AN equals the first term in the sequence times the ratio raised to the power of the previous position number. So when we plug that in, we know that A1 is the 1024. And we know that our ratio is 1/2. And it's raised to n minus 1. So let's calculate that for position 10. All right, so you can see here, we just established that n equals 10 because we are calculating the term for position 10. That's going to be important when we plug that into our formula. So then A1 is 1024. Our ratio is 1/2. And okay, so, and then we raise that to 10 minus 1, which we know is 9. So when you do that with a fraction, find, or you can rewrite that as, that is 1024 times 1 raised to the power of 9 divided by 2 raised to the power of 9. That's how you work exponents with fractions. So let's simplify. That's 1024. And 1 times 1 times 1, it doesn't matter how many times you multiply 1 times 1, you always have 1. And then 2 to the power of 9, I think it's 512. Let me see, 2 to the power 9 is, 512. All right, so this is just multiplying fractions. 1024 over 1 times 1 over 512. So you can simplify that to 1024 divided by 512. And you discover that the term at position 10 is 2. And then they'll start getting negative. But right now they're just 2. So your final answer is your equation plus your solution for the term at position 10. So we would write that as AN equals 1024 times 1/2 raised to the power of n minus 1. And then A10 equals 2. That's your final answer there for number 27. All right, 2 more and we're done, except I do want to sort of show you the formulas in an organized way in case you need them. Okay, so for number 29 and 31, we're asked to write the next 4 terms of the following sequences. So they've given us the sequence 1, -2, 4, -8, and they want us to find A5 through, what they say, 4, A5, A6, A7, and A8. So, okay, sorry, I lost my train of thought. Okay, so first off, you can see that this is alternating positive and negative. So that tells you that 1, you're looking at a geometric formula sequence, and that your ratio is negative, right? Because a negative times positive gives you a negative, but then if you multiply a negative times a negative, you end up with a positive. So we alternate the signs of each of the terms in our sequence. So R is negative. Well, 1 times -2 is 2. -2 times -2 is 4. So we see that our ratio is -2. We also know that you can do this one of 2 different ways. What I'm going to do is I'm going to use the explicit formula to calculate the term at position 5. And then I'm going to use the recursive formula to find every following term after 5. I know we could do it either way, but I just want the practice. So we need to know that A1 is 1. So when we try to figure out the term at position 5, then we know that AN equals A1 times the ratio raised to the power of the previous position number. So if we are calculating the term at position 5, which I have over here. Okay, so let's use this for reference. So A5 equals A1, which is 1, times our ratio, which is -2, raised to 5 minus 1. That gives us, anything times 1 is just itself. So that means this is -2 to the power of 4. And 2 times 2 is 8. Or -2 times -2 is 8 is 4. Positive 4 times -2 is -8. And then -8 times -2 is +16. So we have 16. And then A6, if we just are using our recursive formula, which is AN equals AN minus 1 times R, and AN is 6, then this is 6 equals the previous term, which is 16, times our ratio, which is -2, and that gives us -32. All right, so then same thing. A7 equals the term at position 6, which is -32, times the ratio, which is -2, and we end up with a positive 64. And then lastly, we take for A8, term at position 8, we take the previous term, which is 64, not negative, 64 times our ratio, which is -2, we end up with a negative 128, and then we have all of them. So our final 4 is, all right. So yeah, you can line those up. I got to move on. I got people waiting for me to get out of my classroom. Okay, so our sequence for 31 is 1, -3, 9, -27. So let's find position 5, or the term at position 5, using the explicit formula. Explicit formula is the previous, what is it? Right, the first term, 1, times the ratio, what's our ratio here? -3, right? This is geometric. We have a ratio of -3, and raised to the power of 5 minus 1, which is 4. When you do that, you find that -3 raised to the power of 4 is a positive 81. And so then we use our recursive formula, which is the previous term, AN minus 1, times the ratio, which is -3, and that gives us -243. And again, we have the term at the previous position, which is -243, times our ratio, which is -3, and that gives us a positive 729. And then our last term is the positive 729. It's our previous term times our ratio. And that gives us an answer of -2,187. See, don't those geometric formulas or sequences escalate quickly? All right. So this, it just gives you everything in one place. If we want to look at arithmetic formulas, we have the recursive formula, which is the term at position n equals the, see, this is why I have to do this, because I get my recursive and my explicit mixed up every now and then. So it's the previous term. So the term at position n equals the previous term plus the difference. Remember, you have a common difference. The explicit formula goes from addition to multiplication. It becomes AN equals your first term in the sequence, so A1, plus the previous position number times the difference. Okay. And then geometric, geometric, I'll keep my format the same here. The recursive formula is the AN, a term at position n, equals the previous term, AN minus 1, times the ratio. The explicit form of this escalates from a multiplication to an exponent, which is like that next level. So then you end up with the explicit formula for a geometric sequence being the term at position n equals the first term in the sequence times the ratio raised to the power of the previous position number. So if you're calculating the term at position 50 and n equals 50, that means that n equals 50 right here too. Don't forget that. That's going to be really, really important. That n is always the same. All right, that is it. That is everything that you need. So after this video, go ahead and have these notes. You may use your notes to attempt the quiz. The quiz is quiz over sections 4.5 and 4.6. And good luck, and I will see you later. Thank you.